Okay, we're back at it. In this lesson, which is Chapter 1, Section 3, we're going to look at number sets. Numbers come in all different types and shapes and flavors, and they all fit into different categories. So we call those categories number sets. And we're going to be talking about the different number sets. So we've got counting numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers, and then my favorite are the imaginary numbers. So let's go back up to the top and let's talk about what are counting numbers. Counting numbers are just what they imply. They are, if you have a bunch of things out and you go to count them, well, those are the numbers you use to count things. Now, sets have different symbols to represent them. Counting numbers, or natural numbers, are represented by a capital N, but there's a little twist. There's a double line right there. You see that double line I wrote? That's the symbol for natural or counting numbers. So N is the set of numbers 1, 2, 3, 4, and so on. You just go on to infinity. Okay? That's the set of natural numbers. Now, if you think about it, there's a zero missing. Well, when you go to count something, you don't count 0, all right? But 0's there to represent if you don't have something, all right? So that drops us into the whole numbers category. Whole numbers are represented by a capital W, but it's double barred on these two arms of the W. And the only difference between the natural numbers and the whole numbers is you drop in a 0. So we've got 0, 1, 2, 3, and so on. Okay, so those are the whole numbers. Now, think about a standard number line. Okay, a number line also goes to the left. It goes into the negative numbers. Well, if we add in those negative numbers, then we've got integer numbers. Now, if natural is N, whole numbers are W, you would think integers are I. Not the case. Don't ask me why. But we've got capital Z, and that's a double bar there. So the set of integers is, now you can start at infinity and build up, and then you go -2, -1, 0, 1, 2, and then you just keep going to infinity. So there's your set of integer numbers. Now, what's in between all those numbers? Like, what's in between 1 and 2? You've got things like 1 1/3, 1 1/2, 1 4/5. Well, if you start throwing in those fractions and decimals, that takes you to the rational number set. Now, rational numbers, or the rational set, is a Q with 2 lines in it. And this one's a little harder to explain because I can't really show it on a number line like this. So it's going to take a few more words. Okay, it is the set of numbers that can be written as a fraction. So it's the set of all numbers that can be written as a fraction. Set of numbers that can be written as Now, I could write fractions, but typically you just see this as written as A over B. So that's a fraction, A in the numerator, B in the denominator, with one small caveat, and that is B cannot equal 0, because you can't divide by 0. So that's the set of numbers that can be written as A over B. That's your rational number set. Now, irrational numbers can't be written as a fraction. So that takes us to our second Q set. So Q prime. That's not a 1, that's a prime. And that's the numbers, the set of non-repeating, non-terminating. So the decimal would never repeat. It wouldn't be like 0.121212. It would be just a random bunch of numbers that would go on forever. And if that's the case, you can't write it as a fraction. So we say that irrational numbers are the set of non-repeating so that's non-repeating, non-terminating numbers. And you already know a very famous one. A very famous example is pi. Pi goes on forever and ever. It never repeats, never ends. Another example is if you try and take the square root of an integer, that also, well, not all integers, prime integers, that also never repeats and never terminates. So two pretty common examples of irrational numbers. Now we get into real numbers. Real numbers are any number that fits on a number line. So if you look at a number line and you look between the integers, you see all the fractions. All those numbers on a number line are called real numbers. And that is an R with a double bar. And that we describe simply as all numbers on a number line. Now, that brings up an interesting question. If real numbers are all the numbers on a number line, what about, are there numbers that aren't on a number line? Yes, there are. We have numbers that don't exist on a number line, and we call those imaginary numbers, okay? And imaginary numbers is an I with a double bar. It looks like a Roman numeral 2, but it's an I with a double bar there, equals, and this is the set of numbers not on a number line. So I'm going to say that as numbers not on a number line. Now that's kind of hard to wrap your head around, but they are common and they do get used. If you have a parent that's an electrician, ask them about irrational or imaginary numbers. Electricians use imaginary numbers all the time if they want to change the phase of the electricity going through a wire. A very common one is the square root of a negative number. That would be imaginary. You can't find the square root of a negative number on a number line. So these are the 1, 2, 3, 4, 5, 6, 7 different categories of numbers, number sets. And let's look at how they all fall within each other on a Venn diagram. So we're going to start with the natural numbers. Okay, so we've got natural numbers. They exist as a set. Okay? Now that set of natural numbers exists within whole numbers. So we've got whole numbers. And within whole numbers are natural numbers. Now whole numbers exist within integers. So I've got my integer set sitting here. And integers include whole numbers and natural numbers. Now that set sits within rational numbers. So now I've got my rational numbers. Like that, okay? Now, irrational numbers kind of fall outside all this. We've got Q prime, okay? They're out there kind of on their own. All of which, I'll put a circle around that so you see that's a set. All of these exist whoops. Oh, that's just terrible. I'm sorry about that. All of those exist within the set of real numbers, okay? And outside real numbers, you've got those imaginaries. So this is how these embed within each other, kind of like those nesting Russian dolls. You know, one fits inside another, fits inside another, fits inside another. That's how all these fit together. Now, I want to go back to a couple of the concepts we had here. Set of non-repeating, non-terminating numbers. Well, if you're looking at a fraction, or sorry, if you're looking at a decimal, how can you tell if you can rewrite it as a rational number? That is, if you're looking at a decimal, how can you tell if you can rewrite it in the form A over B? So let's take a look at converting repeating, non-terminating decimals to a fraction. That is, taking a decimal that fits these categories and rewriting it as a rational number. So I'm going to take as an example 0.7777 and just say that just goes on forever, okay? Now, how do I know that I can rewrite that as a rational number? How do I know I can rewrite that as a fraction? Well, here's what I'm going to do. I'm going to say this is my x. So I'm going to go x. X equals 0.7777, repeating on forever. Now, what I want to do is I want to move that decimal between the first and second sevens. Well, if you move a decimal one place, that's the same as multiplying by 10. So I would say that 10 times x equals, now 10 times 0.7777, repeating, is 7.7777, repeating. Okay? All right, so that was my starting number. I wanted to move the decimal one place, and now I'm going to subtract these two. So I'm going to subtract. If I have 10x and I subtract x, I have 9x. And if I have 7.7777 forever, and I subtract 0.7777 forever, what happens is all these cancel each other out, and I have 7 minus 0 is 7. Divide both sides by 9, and x equals 7 over 9. So the repeating decimal, 0.7777 on forever, is equivalent to 7 over 9, which means 0.7777 repeating is a rational number because I can rewrite it as a over b. I can rewrite it as a fraction. Okay, but let's take a look at another example. Let's say instead this time it's not the same number repeating. Let's say that x equals 0.232323. So what's repeating every time are the 2, 3. Okay, now this time what I want to do is I want to move the decimal over 2 places because I want to get it to where you start to see that decimal repeat itself. So if I'm moving 2 places, I'm multiplying by 100. So I go 100 x equals, I'm moving the decimal 2 places, so that's 23.232323. Boom, and that goes on forever. Okay? We subtract these. 100x minus x is 99x equals, now all these decimals cancel each other out, and I have 23 minus 0, which is just 23. Divide both sides by 99. And 99's cancel, and x equals 23 over 99. So again, I took a repeating, non-terminating decimal and rewrote it as a fraction, a over b. So that's how you can